Okay, it's magic time. Welcome, EECS16A. Woo! All right, what a great day. The weather is amazing. Oh, I woke up this morning. I opened the door. Usually it's like freezing and it's just so nice. Smelled like home. I really actually was homesick this morning. It's just like has this like smell of, waking up in Israel in the morning, then it's the weather, then you go to the beach. So I had to call my family. I almost cried. What a great weather. It's so nice. It's you notice there's this strange feeling in you. For those of you that just came to Berkeley, you probably maybe not notice, but for people who live this in the Bay Area for I don't know how long, this strange feeling that you have in your forehead where it's like becomes like kind of wet a little bit when you walk outside. It's like so strange. It's like very hard to. It's like things go like, oh wow, what is this? Moisture on my forehead. Where is it coming from? Hopefully, by the end of this class, we end up wet completely. It's great. Okay. Whoa, it's too strong, too loud. So, I don't know. I mean, I just don't want you to fall asleep because, heat, that kind of stuff. So, I'll try to keep it going. But, today we're going to do some exercise. There's going to be some exercising, like you're going to hold your hand like this. Okay, hold your hand. And just like this. And then you go like this, and like that. And then like this, and like that, right? You'll practice this a lot today when we talk about matrix multiplication. Okay, last time we talked about Gaussian elimination, both the game and the algorithm. And we're done with that. And then today we're going to talk about vectors, which are a really interesting concept. And then matrices and matrix multiplications and a matrix vector multiplication, all this good stuff. And then finally thinking about matrix multiplication as linear set of equations, which we've been kind of emphasizing that it's really useful to solve, right? Right? For example, I'll mention that word in less than 20 minutes. A quick thing about a summary. So Gaussian elimination, pretty simple algorithm. There's actually a pseudocode here that you can kind of follow and think about implementing. But really what you do is you reduce the matrix from a two-row echelon form from the left side to the right-hand side of the matrix using multiplying an equation with a non-zero scalar, adding a scalar constant multiple of one equation to another, and then swapping equations. You play all these tricks, and then you end up with a row echelon form, which is really kind of like a generalization of a upper triangular matrix. So when you actually see something like this at the end, we see ones as the pivots on the diagonal, and then you got stuff over here. That means that there is a single solution for your linear set of equations. It's unique. There is no other one. There's just a single solution for these linear set of equations. When you see something like that, when there's like a 0 on the diagonal, then you'll have infinite solutions. When the line with 0 has a 0 on the other side. That means that you have infinite solutions. Infinite solution means that there is degrees of freedom. Now you might say to yourself, what would you say to yourself? Is infinite solution a good thing or a bad thing?
It's a bad thing.
Raise your hand if you think it's a bad thing.
You want to build a highway?
Hold on. Actually, who said if you want to build a highway? You said?
Yeah.
Is that a bad thing, right? If you have infinite solutions.
Bad thing?
Is it a bad thing or a good thing?
Good thing. Really? Okay, infinite highway.
Well, okay. Who thinks it's a good thing? Infinite solutions. Raise your hand. So less people. Who thinks depends? Like who is like kind of in the middle ground? Okay, well, it looks like there is a center here. There's a left wing. There's a right wing. That's great. That means that this is good politics. Let me argue it really depends. It really depends because let's say I want to solve for the tomography problem. If I have infinite solutions, well, what's an image? I don't know. I don't have enough information to recover my image. Okay, that's not a good thing. You said highway. You want to build a highway from point A to point B. How many solutions do you have? Actually, quite a bit of them, right? Like actually infinite. Because you can go straight, but you can go kind of like around in many, many different paths. You can go backwards and circle a lot of stuff like in a spiral and then come back. There's so many ways that you can go. Now, what would you pick one solution, the other? I mean, you could, if you want to optimize then, like if you have infinite solution, you can optimize for a solution. Let's say the one that minimizes distance. Let's say the one that minimizes elevation, the one that minimizes cost. So there's a lot of solution you can pick among those infinite ones. So sometimes it's a really good thing. For example, let's say somebody wants to build a highway, and you say, oh, there's one solution. You have to really just rip out 1 million people in order to do that. Well, that's not a good thing, right? But if there's other solutions, then you might want to minimize that damage. Okay, so infinite solutions, this is this situation. And if you actually have something that's non-zero over here, so it's kind of here, then there's no solution. It means that you have some inconsistency, right? There's some inconsistent set of equations there. That is problematic. There is no unique or explicit solution for the set of equations. However, there might be a good approximate solution. We'll talk about that when we talk about least squares towards the end of the class. Okay, so there might be, that's not necessarily a bad thing because often you'll have that situation when there is no solution. And you say, okay, but I'm going to find like the best one. Okay, so that would come up. But when you do Gaussian elimination, when you reach this, you go like, stop. Okay, there's no point in continuing. And then for these two cases, what you can do is back substitute to reduce to row echelon form from the right hand to the left hand in order to make it as diagonal as possible. And then for the single solution is going to be a diagonal, and like that means that that's pretty trivial. Whatever you have here will be the solution for x4. Whatever you have here will be a solution for x3, and so on and so forth. And then this, in the case of infinite solution, and the nice thing about that, it will reveal to you which is the free variable and which are the dependent variables. Now, we call the diagonals pivots, and then the ones that have ones on the diagonals, then we call them basic variables. And then the free variables is those that we can actually choose. And every basic variable depends on the free variable. So once you decide on a free variable, 5, 45, 48, I don't know, somebody picked some number, then the rest are dependent on that. And that sets the solution. So once you pick one value, then the rest falls. Okay? But you have a degree of freedom to pick this one value. Okay. That was kind of a summary. You'll crunch lots of Gaussian elimination stuff, both in homework. Discussion was, oh, you didn't have discussion yesterday. So next, like tomorrow, you're going to do some practice on that, and we're going to give you enough homework problems in order to do that, and you can practice more and more and more and more. But what I want to talk about is this beautiful construct we call vectors. Okay? All right, what are vectors? Well, an array of n numbers, okay, that represents coordinates in an nth dimensional space. Okay, it's just pretty much you take n numbers and you put them in this mathematical form. This is the first number, this is the second number, and all of them till you get the nth number. And you take this x and put out like an arrow on its head, and you call this a vector. Okay? So if I write this, then that represents this. That also means that x, this vector x, is in Rn. What does it mean? Well, it's n real numbers, in the reals. Now, what about complex? one of you might ask. Oh, thank you. What about complex? Well, it could be. It could be complex. That will be C. X will be in C of n, in the complex space. However, in this class, we're not going to deal with complex numbers. You're going to deal with complex numbers in 16b. Okay? Extremely useful concept by itself. All right. Now, for example, we can pick a two-dimensional vector, let's say 3 and 2, and that means that x is in R2, which actually I can now draw, because R2 is easy to draw. If this is x1 and this is x2, then I would basically have... oh, by the way, an announcement I have. No office hours today. I have to check this hand. So, and unfortunately, Anna is not around. So, yes. No lab this week. I want to say no, and I want to say maybe. I don't know. Whatever is in the calendar. It says no in the calendar, so the calendar is spoken. I am less authoritative than the calendar. I do have authority to change the calendar. But if the calendar says so, it means that I didn't exercise my authority. Okay. So this is 3, and this is 0.2. And means that now I can draw this beautiful vector. And this vector here represents now an arrow or something that points in two-dimensional space, this point in the two-dimensional space. Okay? All right? That's great, but it's so much fun, oh, two-dimensional space and stuff. But really, what do vectors mean? What does vector mean? What do those numbers mean? Do they have a meaning? Like, what is this? Look at those vectors like 3 and 2. What is this? It could be direction, it could be magnitude, it could be coordinates, coordinates on a grid. It could be, you said like direction, that's fine. Force, could be force that somebody's applying in X and Y, that could be, right? It could be many things. And when you actually put numbers in an array, they can represent many, many things. Here, let me give you an example of a three-dimensional vector, right? You open your thing, this is on a Mac, you open and you want to set up a color, and that color is my favorite color, kind of pink. Is that pink or purple? Pink and purple? Somewhere in between. And basically, this is a combination of red, green, and blue. How much? Well, 215 out of the red, 131 out of the green, and 25 out of the blue will give me this beautiful, beautiful color that you see here. Okay? So that is a representation in a three-dimensional space of colors. Nice, right? Okay. What else? What else I can use vectors for? Who said imaging? Oh, nice. Well, you forgot the magic word, tomography. Right? I told you less than 20 minutes. It's going to show up. Okay, so pixels in an image can be represented by a vector. I'm waiting for the question. Yeah. Oh, why not represent it as a matrix? Because it's two-dimensional, right? It's a good reason for that, because often we would apply operations on images. It's much easier to write that as a matrix times a vector, as opposed to a matrix times a matrix as a matrix and things like that. So it's a little bit more complicated if you want to apply some operations. But so that's why what we do, hold on, just give me 1 second, is that you would take those pixels in the image, for example, and rasterize them somehow. If you like the C programming language, you would rasterize them with a row first. If you like Fortran, then you would do row first. Okay, pick your favorite language. Python? Python actually uses a row first, like it uses the C convention. The what? I don't know. Anyway, so you rasterize them into vectors. What was your question?
When you rasterize them, how do you retain the information about when the row stops?
Okay, so when you rasterize, how do you return that information? You obviously, when you write a function, you would save those values of what is the size. But otherwise, it could be just represented as a vector. It doesn't mean that you need to change the values. Actually, the way image is stored in memory, if it's stored continuously, it is rasterized. Right? Like in memory, it would be just a continuous portion of memory that is already rasterized, whether it's rasterized in the C convention or is in the Fortran convention, row or column first, is already rasterized by itself. Okay, so but you know that it comes from a two-dimensional orientation. And of course, if you want a volume, then it would be rasterized too. But it doesn't have to be. It could be, here's the number of sunspots every year since the 1900s. Correlate really well to sun activity, and you see the cycle of 11 years that the sun has. And now we're actually peaking like in the middle of the next cycle, which is not drawn here. We're kind of like, it went down and we're like around here. So sun activity is picking up. If you care about it or not care about it, that's your problem. But I do care about it a lot. It actually has to do a lot with radio propagation. So if you're like amateur radio like me, then you love the sun to be active but not too active. And if you want your utilities to still work, you want the sun to not have like these crazy coronal mass ejections that can actually destroy humanity. Okay? Which could happen because there was an event in 18-something called the Carrington event that it was just when telegraph started that telegraph lines started sparking, like emitting sparks. Imagine if that would have happened today, we would have gone back to the Middle Ages. Special vectors. Well, must have special vectors. All vectors are good, but some of them have names. This is the 0 vector. Has all zeros. So when you just write 0, sometimes people will just write 0 as for a vector, even when they mean a vector. But here, trying to make sure that it has a line on it, an arrow. This is the 1 vector. It has all 1s. And then you've got the identity vectors. E1, which has 1 in its first entry, and then the rest zeros. E2, which has 1 in its second entry, and then the rest zeros, and so on and so forth. Okay? Now, why do you use them? Because these vectors are actually representing coordinate system, right? Like the natural coordinate system, or the natural axes. So the x-axis, the y-axis, and if I had the third, it will be the z-axis, and so on and so forth. All right, we're done with vectors. That was easy. Are you ready for the next concept? Now, here's the thing. With mathematics, I talked about syntax sugar. Having these constructs in mathematics that allow you to represent complex things simply, in simple notations. And then sometimes all sorts of operations that seem like, simple for you, let's say when you're working on scalars, would then translate into, more advanced stuff like matrices and vectors, and vectors and matrices and so on and so forth. We'll be able to use some of them, and you'll see that, oh wow, I can write it now like this complex thing in this like 2 just letters. It is extremely powerful. When I talk to I'll explain it. But what are matrices? Well, matrices are, instead of a collection of numbers that are in a column, now they're number in a rectangular form. Right? What a great invention. You often use capital letters, to represent matrices. Not all books will do that, but we'll try to be consistent with capital letters. And in that case, x would be in the R n by m. What does that mean? So it's reals. And the size of this rectangular object will be n values by m values, meaning that I have n values here and m values there. And the elements have two indices. The first one is for the where you are in the column, and the second one is where you are in the row. Okay, that is the notation that we're going to be using. Who's bored? It's okay, just fine. We're developing a language here just to make sure that we speak in the same thing, because different books will have different notations, different places, different classes if you've taken will use something else. So we're just developing this language so we can be able to talk. Okay, now here's the, hold on. Let's just ignore this for a second. What does this look like? And I'm going to move this thing over here so it kind of looks like that. What does this look like? It looks like a vector. So a matrix is a concatenation of vectors also. And I can write the same matrix, the same thing that I've written here in this x1, x2, all the way to xm. What's the size of x1? It's an n November length vector. How many November length vectors do I have? Mike of them, right? M. Okay? All right, beautiful, beautiful, beautiful. Where am I going with that? Oh, let me argue then that a vector is actually a degenerate matrix, right? It is a degenerate matrix. A vector is a matrix which is n by 1, right? A vector is a matrix that is n by 1. And you know what? A scalar is also a matrix that is 1 by 1. That's an interesting thing to go backwards in thinking about that way. Because once we define things for matrices, you'll see that it goes down. And like sometimes it's easier to think in scalars because you've thought in scalars for most of your lives. So kind of go back and see, what does that actually mean? Let's just make this matrix a scalar, see what happens. Let's make this thing a vector, see what happens. Okay? Great. Okay, so then you've got these vectors. Like we had scalars, what do we do with numbers? We can add them, we can multiply them, we could divide them, you could apply operations on them. And that is an important concept. And so vector addition is one thing that we do. So two vectors of the same length can be added. What happens if they're not in the same length? What if they're not in the same length? Whoa. What is this? Got all these texts. No, that's not what I'm looking for. I think it's this thing. Oh, yeah. So what happens when you start to add them and it's not in the same one? It's not in the same length. It's a sad thing. You can't do this. So if they're not in the same length, then you can't add them. Right? Somebody will cry when you start doing that. And the first person that would cry is me. Okay, if I see that on your midterms. Okay? So the addition is done element-wise. That means that you add two things. Okay, so let's look at x plus y, for example. So I have a vector x, and this is the vector x, and the vector x is 3 and 2, so this is the vector 3 and 2. And what is the vector y? Is 1 minus 2. 1 minus 2 is pretty much, this is 1, and minus 2 would be here, so it will be this way, right? Oh, so it's minus 2, 1. I'm just reading it backwards. Minus 2 and 1 is this vector, right? And I want to add them together. What does it mean to add them together? It means that I'm going to take now this vector, and then instead of writing it from here, I'm just going to write it from the end of the other vector. And that will be the result. Okay, so just doing that. And the result would be then 1 by 3, right? That would be the result of this addition, 1 by 3. Okay? So that's great. Fabulous. So, yeah. So that will be the result. And then it's really pretty much just adding the values on the order. So you take a 3, 2, and a minus 2 and 1, and you add 3 and minus 2, and you take 2 and minus 1, you add them, and you get 1 and 3. Now, look, this is how I define vector addition, but maybe there can be another weird operation that I can call addition that does something else, right? I mean, I could invent something for how to add two things, right? There's many ways, perhaps, that you can add two things. In this case, we're going to add them element by element. Now, the nice thing about this is that x plus y actually commutes, so I can replace those operations, and I can do y plus x, and it will be exactly the same thing. And so if I draw y, and then from its end, I'm going to write and draw on x on top of it, you'll get to the same point. It doesn't matter if I draw the first one first and then add, or the second and then add the first. So I'll get the same result. And of course, that makes sense, because if I take minus 2 and 1, add 3 and 2, that'll pretty much have minus 2 and 3 on the top. And we know that when you do scalar addition, it commutes. Hence, this should work, and I get 1 and 3. Okay? No new thing here. But you know what? It's going to get a little bit complex, because we're going to do multiplication, we're going to do all stuff. So just remember that vectors, you can only add from the same size, and addition commutes. Okay? So properties of vector addition is commutative. There's also associative. So if I first add x and y, and then I add z, is the same as first adding y and z, and then adding x to the result. So the order doesn't matter. There's also additive negative. There's always a negative vector. So there's an x and there's a minus x. And when you add them both together, you get the vector 0. Ha! And there's additive identity. If I take x and I add the vector 0 to it, it also gives me back x. It doesn't change x. Okay? These are definitions. We're going to have a bunch of definitions coming up when we talk about span and vector space and that kind of stuff. So, and some of them we're going to prove, and some of them not. Okay. So what else you can do to vectors? I can multiply them. Well, I can multiply with a scalar. That's something that we can kind of maybe, understand. So if I take a scalar and multiply by the vector x, it's basically multiplying each one of its elements. Okay? All right? That's simple. So for example, if I have the vector x, which is 3 by 2, this is the vector, and I multiply by 2, what it would do, it will scale each one of those elements. So I'm going to get 6 by 4. And this would be the result. Now, what happened? What changed and what didn't? Magnitude changed. My arrow is longer. Why? I multiply by 2, arrow became longer. What happened else that has not changed? Direction. If I multiply by a scalar, the direction of the vector doesn't change. Now, what if I multiply it by minus 2? It will go in the other direction, but it's still on the same line. Okay? So whether it's in the negative or positive, we still consider it not changing direction. So in that sense that it stays on the same line. Obviously, it's going backward. Okay. So multiplying by a constant only changes either just scales it pretty much. Scales it, whether it scales it positive or scales it negatively, but it just scales it. Right? The angle of that line where the vector lives doesn't change. Okay. Ooh, that's a good one. You stand, and then you go like that. What just happened? One of my favorite operations, transpose. Vector transpose. Is that useful? Oh my God, it's useful. Okay, so what is it? What is this operation transpose? Is transpose valid for scalars? Is it? Who says no? Valid for scalars. Is transpose valid for scalars? It's like, can I apply a transpose to a scalar? Like, am I going to have the cry, or I'm going to like, oh, okay, computes, compiles? Does it compile? It will compile. It will compile. Why? Because scalars are actually degenerate vectors, right? Yeah. Okay, what is a transpose? Well, a transpose is you put a t on top, or you put sometimes a prime. That's another way of writing the same thing. So, sometimes people will write like that. I don't know if you ever seen like a star or an H. That's also kind of like a transpose. For the reals is the same, but if it was complex, it would have been different. Okay? So some of that notation you'll see, but all of these for the reals represent exactly the same thing. And what is, if x is a column vector, which is a n by 1 vector, then x transpose would be a 1 by n vector that is just on its side. Okay, you just replace those elements that way. Yep. What? The transpose of that? Yeah, it would be then x. X transpose would be back x. Yeah. So you can transpose both, absolutely. Now, when we write in convention x with an arrow, we mean a column vector. It's defined as column vectors. Okay? If I want to write a row vector, I'm going to write x transpose. And sometimes, because space is limited on exams, we would write let x be 1, 2, 3, 4 transpose. Why would we write that? Save space, because we're not writing in ancient Japanese where things are in a column. We're writing them, actually it's not ancient, like even today they write something in columns. We write it, in rows, and then that's easier to fill space. So this actually means a column vector, because I have a row vector that's transposed, answering the question that we had before. Okay? So that notation is extremely useful. Now, why we can apply, what would be then the transpose of a scalar? Itself, it doesn't change. Right? So transpose of a scalar doesn't change. Okay, now let's go to matrices. Matrix can also be added together. And what type of additions you can have? Well, the addition is, again, element-wise. Shh. The addition is element-wise. I had this like beautiful sound effect, and I just can't find. Oh yeah, I found it. Okay. And then, what if you try to add two matrices with different sizes? No. You do not add two matrices with different sizes. Okay? That just doesn't compute. When you go like compile, doesn't compile. All right? So, how do you add them? I'm just going to write. I can't. It's really painful. So I'm just going to write it. Okay? So in this case, here, minus 2 plus 3 is 1. 1 minus 1 is 0. 1 minus 1 is 0. 3 minus 2 is 1. And I ended up with this matrix, which actually turns out to be also a special matrix. It's a diagonal matrix. And beyond being a diagonal matrix, it's the identity matrix. And the reason I'm opening my I is because often it's like I. You write it as I. The letter I. The letter I is often used to represent identity matrices that have ones on the diagonal. Okay? Scalar multiplication is again the same. You scale all the elements by that scalar. So that goes back from, there's nothing special that translates then from the vectors. Yes?
Is there any special relationship between x and y that makes it the identity matrix, or is it just a coincidence?
Oh, in this particular case, there's no relationship between those x and y's. They end up resulting in the identity because I wanted you to show the identity and I didn't want to have a special thing for it. So then I just added those numbers that will result in identity so I can talk about the identity. But of course, it doesn't have to be identity. It could be arbitrary value. Like for example, if this was if this one was minus 3, then it wouldn't be an identity. Still would be diagonal. Okay. Now, if you remember, this was vector transpose. What can I do? Can I apply transpose now to a matrix? Can I? Hell yeah. Of course I can. So, if the element of the matrix A are R n by m, November by Mike, n by m, and the elements are A, I, J, then the elements of A transpose, now A transpose belongs to R m by n. The sizes change. If I had n by m before, after transpose operation, suddenly I have a matrix which is different. It's an m by n now. So its size have changed. And the elements are A, J, I. So I flipped those indices. Okay, I flipped the indices between x and y. Like the first index is now the second, and the second is the first. Check this out. This J goes and being first. And this I is being second. Okay, so you flip those indices. Isn't that awesome? Well, how do you think about it? Well, if this is a matrix, and the matrix is composed out of vector A1, vector A2, all the way to vector AM, what's the length of each one of those vectors? I have m of m. What's the length of each vector? N of m. And when I transpose, then it's like stacking A1 transpose on top, A2 transpose below, A3 transpose below that, AM transpose below that. And so now this matrix is m rows and then n columns. Okay? So that's how we think about that. Okay, so A now is n by m, and now the result of A transpose is an m by n. Let's do a simple example. If I have 0, half, half, 1, 0, 0, what will be A transpose? What will be the first row? 0, half, half. Why? I took this vector and I wrote it transpose. And now I take the second vector, 1, 0, 0, and I write it as 1, 0, 0. That is the matrix transpose. So if this is this one, and this one is this one. Okay? Yep.
So is transposition a linear transposition? Does it preserve something?
Well, it changes things. A transpose plus A, for example, sometimes is not possible. Right? But A transpose plus B transpose, if A and B were the same size, yes, they could be added. Okay, so that's what we've seen. Now we're getting to the good stuff. Multiplying two vectors or multiplying two matrices. When we're scalars, don't think about sizes. Take A, take B, smash them together, you multiply A by A and B, A times B, B times A, no problem, right? No problem for scalars. Let's do a game. 2 and 4. 2 times 4. 8. 4 times 2. 8. Same. And you could do it. No crying. No crying. But multiplication is for vectors, and matrices are only for specific matching dimensions. The width of the first needs to match the length of the second. Now, when I took linear algebra, I don't even want to say how many years ago, because then you think, oh, it's like, oh, dude, it's going to talk about it. Just like, I had this amazing, I'm not going to say when. You can guess. But I took a linear algebra actually from a math class in my first year. It was algebra A, whatever, something like that. And we had an instructor, and that was kind of the temperature in the class. And the guy was always wearing a jacket and had a tendency to sweat heavily. And was also talking like that all the time. Like this and like that. And that's exactly what he was said. But he taught me how to multiply matrices, and it just burned into my brain. And he said the following. Matrices, I'm translating from Hebrew. Okay. Matrices you multiply like this and like that. Okay? Like this and like that. Why is it helpful? Because, actually I still do it when I multiply matrices sometimes, because I kind of like, oh, is this column multiplied by this row? It's just like, just to track what's going on, do like this, like that. It works. So I'm going to teach you it like this and like that. Okay? That's what we're going to do. So, you can multiply matrices only if this, or vectors, if this length matches this length. Okay? You cannot multiply two matrices, two vectors like this. If this is x and this is y, you cannot multiply them like that. But you can multiply a row vector with a column vector. And you go like this and like that and multiply them. So their size have to match. Now why it's useful to use the hands? Because it helps you track which indices are multiplied with each other and then summed. Okay, so the operation of multiplying two vectors is an operation of multiplication and summation. What? You said multiplication? No. Multiplication of vectors would be multiplication and summation. Okay, you multiply coefficients and then you sum the results. Okay, that's how it works. And you put your hand like this. Come on, do it, come on. You can do it, come on. You wake up, it will help you wake up. It's childish, I know, it's like you're adults and stuff, but it's really helpful because your brain is fried because of this temperature. Okay, so you go like this. You see where your, what do you call this finger? Thumb. You see where your thumb is? And you see where the pinky is, right? Your thumb is on the left side of the vector, your pinky is on the right side, and all the other ones are touching. Let's say you have like 1,000 fingers, because let's say 1,000 length vectors. So you multiply, you take this and multiply like that. There you go. So what it means is that this element, the first element here, will be multiplied by the first element from here. Okay, so your thumb goes from here to here. And then your pinky is going to be multiplying this one with this one together. And then once you perform these multiplications, there's, in this case, was 1 and 2. Let's say it was a 1 by 2 and a 2 by 1. Then you would add the results of these two. That is vector multiplication. Okay, we're gonna do it. Here's an example. Like this and like that. He used to have this voice, and he goes like, "Kacha vekacha." Like it just burnt into my head. And it's funny. I have some friends on Facebook. Facebook, you know, that Meta thing. And you know, from undergrad, and then I just put this picture, and then all of them will go like this, like that. You know, it's just because I also remember. It's memorable. Okay, so if I have two vectors, of each one of them is Rn by 1. If I want to multiply, I cannot multiply y by x. I can take the transpose of y, which will create a row vector, and multiply by x. That is valid. Why? Because then y would be 1 by n, and x would be n by 1. Then this dimension fits this dimension, and that works, like this and like that. So that's always a way to check. If you don't remember which one, you go, yeah, fits, okay. Computes, compiles. Okay, so what will be the result? You go and you touch y1 with you set thumb, and then you touch like that. And then you touch the thumb with x1, and so the first product is y1 times x1. Then you take your second finger, right? Take your second finger. Where is it touching? Y2. And then like that. x2. And then y2 is multiplied by x2. Now you take the third finger. What? What? You take the third finger, like this, and like that. And so you got y3 times x3. And then at the end, you have got the pinky, right? So you add them all. You put them all. And then you add. And then you add. Wait, so you have products, and then I add them. Each one of them are scalars. Yeah, I can add scalars, but what's the result? It's a scalar. I took two vectors, I multiply them somehow, and I got a scalar. Whoa, something changed. It's a different entity. This is called but we're going to talk about it in module 3. Okay, inner product is module 3. Right now it's just two vectors multiplying with each other. Okay. Interesting, right? Wow. Started with like many numbers and ended with one. You know, this is so important operation. Who is taking CS16A? Who's taking it? Who will take it? Think that will take it? All of you will take it. Yeah, you'll learn CS16A. It's a very important class on computer architecture. You know how computers work. And you know that at the, you can write in C, programming language, all that stuff. But at the end, it's assembly language. It's like machine language at the bottom. And there will be like the most basic instructions that the computer will do in the hardware. Okay? And some of them are add, some of them are multiply, move from one place in memory to another. But because the operation of multiply and add is so useful for numerical algebra, then people have implemented in many processors an operation that does multiply and add in the same computer cycle. Why? Because it's faster then. It saves you half the time, because you know you're going to add, right? So it saves you cycles. So it's such an important operation, multiply and add. Okay, so we know now how to multiply matrices, vectors. Now what about matrices? Well, what about the case where we have a matrix which is, let's say a matrix and a vector, right? Like let's not go and just like, I didn't bring my helmet, but like, just like hit the wall immediately. It just slowly move like this. You see, it doesn't hurt, so let's just go slowly. We did vector times vector. Now let's do a matrix times vector. And this vector here, this matrix here is an m by n, and the vector is n by 1. And I want to multiply them. And the question is, what the heck is the result of this operation? Now, is this an important operation? Hell yeah. Like, sometimes when I talk to my students, like on research stuff, really, I work on MRI, magnetic resonance imaging. Sometimes the first thing that we put on the whiteboard will be A times X. We always do that. We put A times X. Now, why do we put the same thing? I just keep the A times X because we use it so much. Just A times X. So, does this compute? How do you know? I don't know. But what you could do is say, well, you know what? The first row of the matrix A is a vector. At least, I can take that vector and multiply it with a vector, right? At least. Does it compute like this? And like that? And yeah, compiles. So obviously I can do that. So I'm going to do like this and like that. Okay. So now I've got the elements and I've got this, and I want to understand what will be the result. I don't know what will be the result. What's the size of the result? Let's try to figure out what the size of the result would be. Well, I'm going to first compute the first one, right? Just take the first row and go like this, like that. Do it. But aim at the thing. So you kind of like, okay. What does it mean? Well, A11 is multiplied by x1, A12 multiplied by x2, and A1n multiplied by an. So you see that the second index will increase, and there's only one index here will also increase, right? And they'll be added. So I'm going to get A11 x1 plus A12 x2 all the way to A1n xn. Okay? So the second index of the matrix is increasing along with the index of whatever we multiply with. Okay, now I've got other rows. What I can do with the other rows, they're still vectors. Can I multiply them?
Yes.
I could. And I should, and I would, and I will. So I can move my hand. Oh, by the way, sorry, I forgot. This is the same as taking this times x, or I can say, how about we call this y transpose, y1 transpose. I can do that, right? I just called it y1 transpose. Why not? Right? So the same thing can be just written as a matrix vector multiplication. Does that make sense? Okay. All right. Now, if I move down, one row, well, now I still have a vector, right? So I've got a vector times a vector, a row vector times a column vector. Can I multiply them? Compute? Let's compute it. So now I'm going to take like this and like that. Do it. A21 is multiplied by x1. A22 by x2. Point out that now the first index is constant, and then the second index changes. So the result will be A21 x1, A22 x2, all the way to A2n xn. Now where the first index is 2, because we're at the second row. Okay? Second row, and here the sum is only of the second index of A is changing. And then I sum them all. What is this? Matrix, vector, scalar? Scalar, right? Scalar. What is this? Another scalar. Now I can keep going, right? I go like this and like that, and then like this, second row, like that, and then like this and like that, like this, 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 this, that. Right? That's the order. You start top, this. Second, like that. Okay, helps thinking about that. So I can just keep going and do all of them and fill the result. Yeah? Y vector is always a column vector. Transpose is a row vector. No. Y is always, like, Y vector is always a column vector. When I do a transpose on it, it's a row vector now. Does that make sense? So basically what I'm saying is that A11, A12, A1, 3, okay, I can't write. A1n, that equal to Y1. It's really pathetic, but I've tried. Okay? Oh. 3 more weeks, and maybe that will be fixed. Yeah. Whoa! Did a matrix vector multiplication create a new vector? It did. What's the size of the new vector? Different. We started with an n-length vector. We multiplied by a matrix, we got an m-length vector. The vector has been transformed. Maybe I can call A a transformation. It does something. It does something to the vector. It changes its values. It's an operation that is applied on that vector that results in some new thing. We'll learn about that. What are the new things? And analyze them. You'll see that matrices can rotate, scale, squeeze into small dimensional space, embed in a higher dimensional space, all that kind of good stuff. We're going to talk about that. Yeah.
I was wondering if a scalar can be written as a degenerate vector, and you can multiply a matrix by a scalar. You couldn't multiply a given n by n matrix by a 1-by-1 vector.
Yeah.
Does that mean there's something inherently different writing A as a matrix or a vector versus just as a scalar?
Yeah, for scalars, it doesn't. Scalar, I mean, if you had written the scalar, right, as a matrix, I mean, A times M is okay, because then the sizes are fine. Is the size? No, scalar times a matrix is different. Okay, scalar times a matrix, we defined it, is different. Okay, it would be element-wise scaling. That is scaling. If you had written, it's like let's say A is a parameterized something, and it could be a matrix. It doesn't work.
Yeah, so that's what I'm wondering. Is it different to write A than a scalar versus a 1-by-1 matrix?
Like we have like a rule specifically for scalars that can multiply. But sometimes we can think of them as degenerate matrices, but we're allowing them because they're special, because they're 1-by-1 to be written as A times M, for example. That's a good point. So the point is that the result was 1 by M, M by 1. Very interesting, very interesting. We got a vector. Okay, we got a vector. Vector of different size. Very interesting. Now the real question is, okay, well, what about this case then? What about 2 matrices now? One is an m by n and one is an n by l. Can I multiply these two? What do you do? Like if you're unsure, like this, like that, right? You put your hands, you go, it's like n. Like that, n. Computes. Computes. That's pretty much it. That's done, right? That computes. So now what I can do is perform this multiplication. Now you got like these two dimensions, right? Before I had rows and I just went down. Now I have a little bit more complicated. So let's just go and see how that works. It also goes like this and like that, like this and like that. Okay? So the first thing we're going to do is we're going to do what we know. We take the first row and we multiply by the first column. What is the result? Like this, like that. A11 times B11, and so on and so forth, right? So A11, B11, A12, B21, all the way to A1N, BN1. Like this and like that. Now the question, what would you do? What's the second? I mean, I can do whatever I did before. I can go down in the thing. Or I can just go to the right and take the first row, multiply by the second column. Let's do that. So basically the operation will be like this, like that, like this, like that, like this, like that, like this, like that, like this. I told you, a good exercise. That. And I want to be really sweaty. Like this, and then all the way to the end. Like that. Okay? So this is how I'm going to fill the second value over here. This was a scalar. Now I'm going to get a second scalar next to it, which is going to be A11, B12. What has changed? What have changed? That the second index of B is 2 now. Okay, the B's have second index. Now it's 2. And then you keep going. And then you keep going. Like this, like that, like this, like that, like this, like that, all the way that you fill all the elements till you get to this vector times this vector. And now, after you've done that, you go to the second row. So it's 2 nested loops. If you're going to implement this, you have 4n goes to, well, not n. 4I goes to from 1 to m, and then 4j goes from 1 to m. And then you do these 2 nested loops. Does that make sense? Okay, so you go now down by 1, and then the first, and then you get this value. And then sweep all the way, so you get the second row. And then you do like this, like that, like this, like that, all the way till you get to the end. And then the last one will be this result. AM, B1, B11, AM, 2. So you see that the first index of A is the smallest, it's the M. And then here at the end, you get MN and B and L, like the corners of that operation. Okay? And just remember, it's like this, like that, like this, like that. Okay? So now, once you know this, and you know like this and like that, let me ask you, I'm going to show you these 2 matrices. I'm going to ask you, I don't want you to compute the whole multiplication. Just tell me what will be the result, okay, at index 2 by 2. So can you compute just this directly without computing the rest? You know what you do? It's so simple. You go to this vector, the second, and then you go to the second here, and you do like this and like that with those two, and that's it. Done. That will give you the 2 by 2. Yes?
When you're computing like 2 by 1, 2 by 2, 2 by 3, like etc., do you add or multiply the results together?
No. So whenever you do the vector, then you multiply and add. But when you move to the next one, it's another index. Right? So you move. So the result here is what? What is this result? This is a vector, this is a vector, these are vectors, right? So there's many vectors stacked next to each other. It is a matrix. What's the size? The size is M by L. Okay? So the first thing that you do is you go, can this be computed? You look at this, match. We can multiply them. What is the result size? M by L. Okay? So if you take an M by N multiplied by L by N by L, you'll get a result which is an M. This is an M? Oh my God. M by L matrix. So two matrices multiplied together, you get a matrix. Yeah, the outer loop, yeah, it doesn't really matter if you go this way or that way first. It doesn't matter. One of them will be M long, one will be L long. Yeah. What if I wanted to find what is this value? Again, what if I wanted to find what is this value? How do I do? You look at the column, and the rows. So you take this row, and which column on the second matrix? The first one. Why? Because that's the first, the M index by 1 of the resulting matrix. Okay? So now you know how to compute any element in a matrix. 2,369 by 5,562,354 in a Google search matrix. What's the value? You just take this column, pick this column, multiply, done. Pretty good, huh? Awesome. Okay. So, here are the rules. In order for it to compute, if I have A times B, these need to match. Like this and like that. They need to match. The second, this size needs to match this size. And if you have an M by N, N by L, the result will be an M by L. So it's kind of cool. Like these kind of match, and the result will be the outer ones. Okay? Nice. Fun. Okay. What? So now, let's go back to vectors. Remember that we took a row vector multiplied by a column vector, we got a scalar. What if we commute them? We take, instead of y transpose times x, we compute x times y transpose. Why not? What's the difference? I just switched the order. Well, when I switch the order, now I want to do like this, like that. What is like this here? It's like a thumb. Only the thumb, right? Because there's only one value. So I take this value, x1, and like that. This is the value. Right? It's kind of like a cross-section, right? Like this is just this part. Like that is just this part. So I'm going to get one element, which is x1, y1. And now I'm going to take like this and like that. And so now I'm going to get x1, y2. And so on and so forth. I get a whole row that is a vector. Woohoo! And now I'm going to go the second line like this, like that, like this, like that, like this, like that, like this, like that. And I'm going to get the second. So when I have a column vector multiplied by a row vector, I get a matrix. Does it make sense by what I said before? Let's see. An n x1 n by 1 times 1 by n. These match, so the result will be a matrix n by n. Okay? The result be a matrix which is n by n. Funny thing, if before we called it an inner product, for this case we call it an outer product. Because it's just the opposite. Yeah.
So when you multiply like a row matrix by a column matrix, are you essentially getting kind of like every possible combination between those numbers?
When I multiply a row vector with a column vector, I multiply the first element with the first element, the second element with the second element, the third element with the third element, and add them together. Here, I get kind of all these combinations that you just mentioned. Yeah, you get all the combinations. Yeah. But you get a matrix, yeah. I don't want to talk about like why we call it inner product or outer product. I'm just mentioning that because you'll see those notation later. Yeah. This one, very special. This matrix, very special. Extremely special. When we talk about rank and spaces and null spaces and all that kind of stuff, obviously something is here. Like you'll see that. Anyway, we'll talk about that. When we talk about linear dependence and all these kind of things of these vectors, then, oh wow, yeah, you know that this is called a rank 1 matrix. I said something. We'll talk about that. It's a very special matrix. But my point is that vectors multiplication does not commute. Matrix multiplication does not commute. Scalar multiplication does commute. Okay? So you cannot switch without thinking about it. Okay? And in some cases, it doesn't even make sense. A times B may not be possible to do B times A just because of the sizes. May not be possible. If they're square matrices, sure. If they're not, no. It will be a very big cry. Let's do that. Ready? The first one, n by m times m by n. What's the size? First of all, compute. Computes? Yeah, because these are the same, like this, like that, works. And the size will be an n by n. Okay. What's the next one? This one. M by n, n by m. Works? This like that. What's the result? M by m. Small matrix now, huh? Interesting. Here was big, here is small. What about this? Works? Yeah, it works because there's a 1 and a 1. What's the result? M by n. That's right. And then what about here? Computes. Second with the first. Yeah, computes. A 1 by m. Beautiful. Let's do it. Come on, open. Let's do some interactivity. So A is in the reals n by L. B is in the reals n by L. Which of these ones are valid multiplications? AB, BA, A transpose B, AB transpose. This is taken from spring something. Okay, 1 minute. Everybody taking the pictures? I'm going to switch. First of all, thank you so much for coming today. Really appreciate it. You do not know how more gratifying is it to teach in front of you than not. I know you have the video option, and I really appreciate that you're coming to class. Hopefully, it'll give you an added value for doing so. Definitely for keeping up with the lectures is what the best way is coming to class. And thank you so much for coming. What? I can't hear it. Yeah, twice it goes back. Okay, here are the results. The results are in. And 84.2 of you says that it's AB transpose. Okay, let's do it again. Now talk to each other and 1 more minute. Talk to each other 1 more minute. Let's see if that changes. All right, vote. There's one small thing I want to show you before we finish. So just finish the vote. Come on, finish. There's only 97 of you. Okay. Hopefully, everybody would have agreed that it's AB transpose. And the reason it's AB transpose is because if you look at B transpose is an L by M. That's B transpose. And then A would be an M by L. And that computes because this element matches with this element. The rest don't match if you try. So just do the exercise if you didn't get it. I just want to talk about this quickly. I have a matrix A and a multiply by X. I did this before, but now I want to think about it as linear set of equations. X are my unknowns. A are some system. And that equals B. Remember AX equals B that we did before? If we write it down, this looks like A11 x1 plus A12 x2 all the way like this and like that, like this and like that, right? That's how it looks like. It's a vector m by 1. And I'm going to say that equals to B. And that's a vector of the same length. Now, if you stare at this long enough, may I remind you that it looks exactly like an augmented matrix that you did Gaussian elimination before. This is linear set of equations. These are exactly linear set of equations. When I write AX equals B, it's a linear set of equations. The same thing. And now, when you write it in this particular way, you know how to solve it. How do you solve it? Gaussian elimination. Not the game, but the algorithm. See you on Thursday.
chance?
What?
Do you work in Skydeck? Because I saw that your hoodie was from Skydeck.
We started a company
Okay.
that was in Skydeck.
Oh, that's really cool.
That
Then I
mo-
applied to like Skydeck like this semester.
You what?
I applied to like